As of the creation of this video, fourth-generation nuclear arms remain purely hypothetical. But what exactly is the concept behind them? The theory suggests that these weapons would generate significantly fewer radioactive byproducts compared to existing nuclear weapon designs. However, they would emit an enormous quantity of neutrons. The critical issue is whether we should permit the development of such weapons and how concerned we should be if we do or if we don't. To address these questions effectively, we must first comprehend the nature of first, second, and third-generation nuclear weapons. Before delving into that, let's clarify two terms you'll encounter frequently in the next 10 minutes: fusion and fission. To grasp the mechanics of nuclear explosions, it's essential to understand these two concepts. Fusion involves combining two or more atomic nuclei to create a single, heavier nucleus. In contrast, fission refers to the splitting of a single atomic nucleus into two or more lighter nuclei. Although fusion and fission are fundamentally different processes, both have played crucial roles in the development of nuclear weapons. With this foundation, let's examine the alarming history of the initial three generations of nuclear weapons. The first generation, known as pure fission weapons, relies entirely on the process of fission. These devices are the most straightforward and least technically complex to engineer and construct among all nuclear armaments. Despite being the earliest and most basic design, they are the only type that has been deployed in warfare. The United States Army Air Force notoriously unleashed a fission nuclear bomb on the city codenamed Alpha at 8:15 a.m. on August 6, 1945. The consequences were catastrophic and harrowing. The majority of the city was obliterated, and by year's end, approximately 90,000 to 166,000 individuals had lost their lives due to the explosion and its aftermath. This event stands as one of the most notorious in the annals of human conflict and marks one of the rare instances when a nuclear weapon was used in combat. But what is the mechanism behind these bombs? The process is termed nuclear fission, which, as the name suggests, involves the splitting or division of atomic nuclei. A neutron is directed at the nucleus of a heavy element like uranium, causing it to fracture into two lighter elements. This reaction liberates an immense amount of energy in multiple forms. Approximately 80% of this energy is emitted as soft X-rays, while the remaining 20% consists of neutrons and other particles. The X-rays are particularly dangerous. When they interact with the atmosphere, they generate intense heat, leading to the massive shock wave we recognize as the explosion. This type of bomb was responsible for the destruction of both Alpha and Beta, and the moral implications of their deployment continue to be a subject of intense debate. Despite the appalling capabilities demonstrated by pure fission weapons, research persisted into the next phase of nuclear armaments. The second generation, termed boosted fission weapons, enhances the already formidable power of fission devices. As the name implies, these weapons incorporate a supplementary mechanism to amplify their effect. A boosted fission device employs minute quantities of deuterium and tritium to initiate a small fusion reaction precisely when the conventional fission chain reaction commences. This synchronization significantly augments the overall reaction. The principal advantage of a boosted fission weapon over its pure fission counterpart is the production of a vastly greater number of neutrons, far exceeding what a standard fission initiator can generate. This intense neutron flux ensures that a larger portion of the bomb's core undergoes fission before the device is disintegrated by the explosion. Consequently, boosted fission weapons achieve yields that can be up to twice as large as those of pure fission weapons. One might assume that this level of destructive power would satisfy humanity's appetite for warfare, but that was not the case. Ambitions grew, leading to the creation of the third generation of nuclear weapons, commonly known as thermonuclear weapons. These are also called hydrogen bombs or H-bombs because they depend on the fusion of hydrogen isotopes, specifically deuterium and tritium. H-bombs function by utilizing the energy from a fission bomb to compress and heat the fusion fuel, thereby accelerating the fission reaction and increasing its yield. The fusion reactions release additional neutrons which supplement those from the fission process, enabling even more fission reactions to take place. This results in a dramatically heightened rate of fission. In essence, thermonuclear weapons reverse the process of first-generation bombs. Instead of splitting a heavy element, they fuse two lighter elements to form a heavier one. A distinctive feature of thermonuclear bombs is their two-stage operation. The initial stage, called the primary, is akin to a second-generation bomb. In second-generation weapons, this would constitute the entire detonation. However, in third-generation bombs, it serves merely as a trigger for the secondary stage. Both the primary and secondary components are encased within an outer metal shell. The radiation from the fission explosion of the primary is captured and utilized to transfer energy, compressing and igniting the secondary stage. Part of the initial radiation is absorbed by the inner surface of the case, which is constructed from a dense material like uranium. Although no thermonuclear bomb has ever been deployed in combat, the United States conducted the first full-scale test of such a weapon in 1952. The device, more resembling an industrial complex than a conventional bomb, was codenamed Operation Thunderclap. The test detonation occurred at 7:15 p.m. on October 31st, Halloween, of all days. The outcomes of this test starkly illustrate the potential devastation of a thermonuclear weapon. The explosion yielded 10.4 megatons of TNT equivalent, with the resulting fireball expanding to a maximum radius of 1.8 to 2.1 miles. The blast carved out a crater measuring 6,230 feet in diameter and 164 feet in depth. Within just 90 seconds, the mushroom cloud soared to 56,000 feet, higher than the typical cruising altitude of commercial airliners. The cloud continued its ascent, reaching 108,000 feet in another minute and ultimately peaking at an astonishing 135,000 feet. The explosion also generated water waves up to 20 feet high, which, along with the blast force, completely denuded the test island of vegetation. This was merely a test, a demonstration of the capabilities of a third-generation nuclear weapon. Fortunately, such a device has never been used in warfare, yet. Nevertheless, scientists and engineers continue to envision and strive for the next advancement in nuclear weaponry, the fourth generation. What does this entail? In essence, fourth-generation nuclear weapons are the polar opposite of the first generation. Termed pure fusion weapons, these hypothetical devices would be hydrogen bombs that do not require a fission primary to initiate the fusion of deuterium and tritium, unlike traditional thermonuclear weapons. For decades, researchers have been investigating methods to achieve the extreme pressure and temperature necessary for fusion without relying on fission. This would effectively be the secondary stage of a thermonuclear bomb without the primary trigger. The primary motivation for developing such a weapon is that it would eliminate the need for fissile material, making it easier to produce covertly compared to conventional thermonuclear devices. Moreover, pure fusion weapons present an intriguing capability. They could be designed to produce arbitrarily small yields since there is no critical mass requirement for fissile fuel as in fission-based weapons. This could significantly reduce collateral damage from radioactive fallout, as fourth-generation weapons would not produce the same radioactive byproducts as their predecessors. If fission could be entirely eliminated from nuclear weapons, we would possess a device with the destructive power of a thermonuclear bomb, but without the long-term radioactive consequences. While the concept is conceivable, its realization remains elusive. After the Operation Thunderclap test, the United States invested 40 years and substantial financial resources into developing a pure fusion weapon, yet no breakthroughs were achieved. The crux of the challenge lies in identifying an alternative trigger mechanism. One proposed approach involves antimatter, which in theory could provide the necessary conditions for fusion. However, the production and containment of sufficient antimatter pose formidable technical obstacles that current technology cannot overcome. Other fissionless trigger concepts include stimulated gamma emission and ultra-high energy density chemicals like advanced explosives. The gamma emission strategy relies on nuclear isomers, excited states of atomic nuclei where nucleons are at higher energy levels than in the ground state. Isomers of elements such as hafnium and tantalum can be manipulated to emit powerful gamma rays, which might possess the energy required to initiate a thermonuclear reaction without fissionable materials like deuterium or tritium. Nonetheless, this remains purely theoretical at present. In our relentless pursuit of the ultimate nuclear weapon, we have progressed from pure fission to incorporating fusion and now aim to achieve pure fusion. Is this feasible? And if so, is it a goal worth pursuing?